Hello, welcome to another module in this massive open online course on the principles of CDMA, MIMO and OFDM wireless communication systems. In the previous modules, we have looked at a basic introduction to a multi-carrier modulation system, and we said that this multi-carrier modulation system forms a basis or is a precursor for OFDM or orthogonal frequency division multiplexing. So, let us now look at two key aspects of OFDM or two key aspects which incorporated in MCM will lead to OFDM, right. So, today we are going to look at the FFT. So, today we are going to look at FFT in this module, FFT and cyclic prefix for OFDM, that is orthogonal frequency division multiplexing. So, we will look at two key aspects. One is the IFFT/FFT processing, one is the IFFT/FFT processing. As you all might already be familiar, FFT is the fast Fourier transform. Fast Fourier transform, and IFTFT is the inverse FFT or inverse fast Fourier transform. And two, the second is what is also known as a cyclic prefix, which is also abbreviated as CP. So, we are going to look at two key aspects in OFDM. One is the IFFT/FFT processing, where FFT stands for the fast Fourier transform, IFFT is the inverse fast Fourier transform. And the second aspect is something unique, which is known as the cyclic prefix. Okay, so, we are going to look at these two aspects, which are the key ingredients or the key steps in OFDM or orthogonal frequency division modulation based wireless communication. Okay. So, now let us go back to our transmitted signal. So, consider the MCM signal. Let us go back to our multi-carrier modulation signal. I hope everyone remembers MCM stands for multi-carrier. MCM stands for multi-carrier modulation. So, consider the MCM signal. So, I have the MCM signal which is xt equals summation of k xk e to the power of j 2 pi k f naught t. Let me refresh your memory. Xk is the symbol transmitted on the kth subcarrier. Xk is the symbol transmitted on the kth subcarrier. E to the power of j 2 pi k f naught t is the kth subcarrier. This is the kth subcarrier. K f naught, this is the kth subcarrier frequency. This k f naught is the kth subcarrier this is the kth subcarrier, this is the kth subcarrier frequency, and we have n subcarriers, total number of subcarriers. The total number of subcarriers the total number of subcarriers in this system is n, right. So, we have the transmitted signal xt is summation xk e to the power of j 2 pi k f naught times t, where xk is the symbol that is transmitted on the kth subcarrier, e to the power of j 2 pi k f naught t is the kth subcarrier, and k f naught is the kth subcarrier frequency. Remember, we said f naught, that is the subcarrier, f naught subset fundamental frequency is basically b divided by n, where b is the total number of b is the total bandwidth, n is the total number of subcarriers. Now, if you look at this signal x of t, let me rewrite this signal x of t. I have x of t equals summation over k x of k e to the power of j 2 pi k f naught t. Now, generating this signal is difficult because of the large number of subcarriers. Generating this signal is difficult because of the large number of subcarriers. Correct. For instance, we are talking about n, the number of subcarriers. So, the number of subcarriers can be as high as 1000, which means for each subcarrier, at each subcarrier frequency you need an oscillator, which means if you have 1000 subcarriers, you need 1000 oscillators. And mind you, these 1000 oscillators have to be precisely placed at that subcarrier spacing, that is 0, f naught, 2 f naught, minus f naught, minus 2 f naught, because only then the orthogonality principle between these subcarriers will hold. Remember, we looked at the orthogonality principle between the subcarriers yesterday, that is integral, that is if I look at f naught integral 0 to 1 over f naught e to the power of j 2 pi k minus l f naught t integrated dt between the limit 0 to 1 over f naught, which is over one fundamental period, is equal to 1 if k is equal to L, is equal to 0 otherwise, right, which means the different subcarriers are orthogonal, and this orthogonality, which is an important aspect of multi-carrier modulation, right, this will hold only when the subcarrier spacing is maintained precisely. Therefore, it is difficult to first have such a large number of oscillators, and further it is even more challenging to have a precise subcarrier spacing with these large number of oscillators, large number of carriers in a physical system. So, therefore, how do we overcome this problem? How do we overcome this problem of a large number of subcarriers? So, how to overcome the problem So, therefore, how does one overcome this problem of this large number of subcarriers, and that can be explained as follows. For instance, let us go back to our initial system. In our initial system, we said that the signal has a bandwidth of, the total bandwidth of the signal is B. So, let us look at the initial system. We said that initial system has a bandwidth of B, which means my maximum frequency f max equals B by 2. So, what are we saying is our signal, our transmitted signal is in the bandwidth B, right. So, the maximum frequency, that is f max, is equal to B by 2. So, it lies between minus f max and plus f max, where f max is the maximum frequency that is equal to B by 2. Now, this is a band limited signal, therefore, I can sample it at the Nyquist rate. The Nyquist rate is twice f max, which is equal to B, right. Since the signal is band limited, since signal is band limited to B, it can be sampled. Therefore, since the signal is band limited to f max, it can be sampled at twice f max, that is the Nyquist rate twice f max equal to B. So, since signal is band limited to f max, it can be sampled at the Nyquist rate. And what is the Nyquist rate? We all know from the Nyquist sampling theory that the Nyquist rate equals 2 f max, which is equal to twice B by 2, which is equal to B. So, what I am saying is, since this is a signal that is band limited, the bandwidth, the total bandwidth is B, the maximum frequency f max is B divided by 2. Therefore, this signal can be sampled at the Nyquist rate, which is twice f max, which is B, right. And therefore, the sampling duration, so therefore, the sampling interval is 1 over sampling frequency. This is 1 over sampling frequency equals 1 over B. So, the Nyquist sampling interval equals 1 over the sampling frequency equals 1 over B, which means, and this, let me denote this by T, which means the kth, which means the lth, let me call this lth sampling instant, or the lth sample is taken at L times T equals L over B. So, what we are saying is the sampling frequency is B, the sampling duration is T equal to 1 over B, the Lth sample is taken as L times T or L over B. Now, let us look at what the Lth sample is. Let us go back to our transmitted signal. I have x t equals summation over k x k e to the power of j 2 pi k f naught t. The Lth sample is at x L is equal to x of L t, which is equal to summation over k x k e to the power of j 2 pi k f naught. Instead of t, I have to substitute L times capital T, that is the time for the Lth sample, and this is equal to summation over k x k e to the power of j 2 pi k. Remember, f naught is equal to b by n times L, t, the sampling duration, is equal to 1 over b, and therefore, now if I look at this remarkably, now if I simplify this further, what I am going to get is, if you take a close look at this, I have summation over k x k e to the power of j 2 pi k L over n, that is equal to x L. So, if you look at this expression, now please look at this expression is x L is equal to summation over k x k e raised to j 2 pi k L divided by n, and this is exactly the expression for the IFFT, right. If you look at the IFFT of the symbols capital X of 0, capital X of 1 until capital X of n minus 1, this small x's, the small x, that is small x of L, is precisely the ith, it is precisely the lth IFFT, that is the inverse fast Fourier transform, or IDFT, the inverse discrete Fourier transform of the capital X's, that is x0, x1 up to xn minus 1. If you look at this expression here, this expression is precisely the IDFT, inverse discrete Fourier transform, or IFFT. IFFT is simply a fast algorithm to evaluate IFFT. The IFFT is simply a fast algorithm to evaluate IDFT. So, XL is the Lth FFT point. So, if you look at this XL, this says that XL, which is equal to summation over k xk e to the power of j 2 pi kl divided by n. This XL is simply the Lth IDFT point, inverse discrete Fourier transform point of x0, x1, xn minus 1, where this IDFT, this stands for inverse discrete transform, inverse discrete Fourier transform, right, x0, x1, xn minus 1, these are the symbols transmitted on the different subcarriers, as we already seen, symbols transmitted on n subcarriers. These are the symbols that are transmitted on the n subcarrier. So, what we are saying is these different samples. So, remember we started out with the problem. The problem is that the transmit signal is difficult to generate because it requires n subcarriers and therefore n oscillators and n modulators. What we are saying is we do not need this requirement. If we consider the sampled transmit signal, that is the samples of the transmit signal, because the transmit signal is a band limited signal, these samples can be generated by the simple IFFT operation or the inverse fast Fourier transform operation, and this is much more simpler than employing n modulators, a bank of n modulators corresponding to the n subcarriers. So, the samples of the multi-carrier modulation signal can be generated by the IFFT operation rather than employing modulators. This is precisely the key principle behind OFDM. This is one of the key principles behind OFDM, that is employing, this is the principle of this is one of the key principle of OFDM, that is I look at the symbols x0, x1 up to xn minus 1 which correspond to the n subcarriers. I generate the IFFT points small x0, small x1, small xn minus 1. These are the samples of the transmit signal. I transmit these samples over the channel. I get the corresponding receive samples. From the receive samples, naturally I can take the FFT, the fast Fourier transform, to recover back the transmitted symbol. So, I do no longer need to modulate on the n subcarriers and demodulate using the matched filter or the coherent demodulation. I can simply replace the transmission by the IFFT at the transmitter. I can take the IFFT, I can transmit the IFFT samples, At the receiver, on the receive samples, I can take the FFT operation to recover back my transmitted symbols. So, I can schematically illustrate this process as shown below. What I am doing is I have n symbols x0, x1 up to xn minus 1 at the transmitter. So, this I use to take the IFFT, that is the sample. So, this is IFFT, this is in fact n point IFFT. So, these are these capital X0, capital X1 up to xn minus 1, these are the transmit symbols on the n subcarriers. The small x0, small x1 up to small x minus 1, these are the transmitted samples over the channel, these are the sampled version of the or transmitted symbols, transmitted samples, the actual samples transmitted, or these are also the sampled version of the MCM signal. This is the sampled version of the multi-carrier modulated signal. Now, these I can transmit over the channel. Now, these samples small x0, small x1, small xn minus 1, I transmit these over the channel. So, transmit these, transmit. So, these are transmitted over the channel. In fact, let me clearly write this, these are transmitted over the wireless channel. So, in fact, if I look at this part, this is my, this box is basically, this box is basically my wireless channel. Okay. And this at the receiver, what do I receive? At the receiver, I receive corresponding samples y0, y1 up to yn minus 1. Now, on these samples, I will take the FFT operation at the receiver. At the receiver, I will perform the FFT operation, more precisely the n point FFT operation, and then I will regenerate my transmit samples x0, x1 up to xn minus 1. All right. So, this is exactly, so this processing is at the transmitter, and this processing is at the receiver. So, in a nutshell, what we are doing is basically it is very simple. We are taking these symbols, the capital X0, capital X1 up to capital Xn minus 1. These are the symbols that are to be transmitted on the n subcarriers. We are performing the IFFT operation and generating the samples of the transmit signal x0, x1, that is small x0, small x1 up to small xn minus 1. These samples are transmitted over the wireless channel. At the receiver, you have the samples y0, the small y0, small y1, small yn minus 1, which are the corresponding received samples. On these received samples, you perform the FFT operation, that is a fast Fourier transform operation, and then you can reconstruct back the transmitted symbols, that is a capital X0, capital X1, capital Xn minus 1. So, therefore, you are performing the IFFT operation at the transmitter and the FFT operation at the receiver. This together, this IFFT, FFT operation at the transmitter and receiver respectively, this is one of the key steps, one of the key principles of OFDM. This is the difference between OFDM and multi-carrier modulation. In multi-carrier modulation, we need to generate all the symbols and subcarriers using modulators, but in an OFDM system, we replace these modulators and demodulators by the simple IFFT operation at the transmitter and the FFT operation at the receiver, and this is the key step in OFDM. This is the IFFT processing. So, what is the key step in the OFDM? That is IFFT at transmitter, correct, and the FFT at receiver. And what is this? This is the key principle of OFDM, which is short for, as you might already remember, again, orthogonal frequency division multiplexing. Right. Now, why is this orthogonal frequency division multiplexing? First of all, remember the different subcarriers are orthogonal, right. Let us go back to the previous lectures to look at this thing. If you remember, we looked precisely at this orthogonality property of the previous subcarriers. We said if you look at these two subcarriers K and L, we said this integral f naught 0 to 1 over f naught e raised to j 2 pi k minus L f naught t dt, this is equal to 1 if k is equal to L, and this is equal to 0 if k is not equal to L, which means the subcarriers K and L, any two different subcarriers K and L in this system are orthogonal, and this orthogonality between the subcarriers is being used to resolve the symbols, transmitted on the different subcarriers at the receiver. That is the first aspect. The second aspect of this OFDM system is, if you look at this, it is frequency division, right. We are dividing this broadband bandwidth B amongst the n subcarriers, with each band having bandwidth B by n. So, this is a frequency division based scheme, multiplexing, which means we are multiplexing multiple symbols over these multiple subcarriers over the bandwidth B. As we have already seen, we are transmitting n symbols in parallel over the n subcarriers. So, we are multiplexing n symbols over the n different subcarriers in the system, therefore the word multiplexing. Together, this is orthogonal frequency division multiplexing. Orthogonal for the orthogonality of the subcarriers, frequency division because this is a frequency division scheme in which you are using multiple subcarriers, and multiplexing because you are multiplexing several symbols, n symbols over the n subcarriers. And as we have already seen in today's module, the IFFT processing at the transmitter and the FFT processing at the receiver is a key step in this OFDM system, which helps easy implementation of this OFDM system. So, let us conclude this module here.